So let me take a moment to introduce Dr. Triston Cao. Dr. Triston Cao leads NVIDIA Graph Neural Network for a deep learning framework and focus on open source project and supports researchers to utilize NVIDIA GPU system for graph neural network application. And in NVIDIA, he also managed various framework teams. And prior to his NVIDIA experience, he was a senior software engineering manager at Cadence Design Systems, focused on EDA software tool development. So that's welcome, Dr. Triston Cao.
Good afternoon. Thank you, Kara, for your introductions. Thanks to all those organizers and volunteers to make this event possible. But most important, thank you all for your presence so that we can share our perspective in this round of AI movement. It is very exciting that we are in a real technology revolutions that impact so many industries, has so many applications. It's ongoing or will be changed for human beings to be better. I work at NVIDIA. Most questions comes to me is to buy or sell stocks. I will not answer that questions. Together, today I will share some of the perspectives, how we get here in terms of software engineering point of view. Next stage. I joined NVIDIA at 2017. Where NVIDIA announced first Tensor Core GPUs. Together with that, there's over 100,000 GPUs named DGX V100. I'm not sure if you're familiar with Jensen Huang's term. The more you buy, the more you save. He will probably announce on the more you buy part, we as engineers to show how do you save. On the top right pictures, there are many products running on those DGX systems named containers. I believe all of them are coming from the deep learning frameworks team that I've been working with for the past 6.5 years. Before that, it was Caffe, was also invented by very talented Chinese scientists and engineers named Yang Qinjia. He has been doing a lot of research on AIs. For the first time, that we can show that researchers doesn't have to spend weeks to train a model. We showed it from weeks to about 5 hours, so that we enable the AI researchers and engineers to do more experiment on their models, to build better AI models on top of it. Let's go, what does frameworks team do? How does you build a framework that enables them? Fundamentally, you build layers of neurons, the information passing from one layer to another, to the last output. And then you use a loss function, a little technical, and you see, oh, this is not good. You found errors there, I'll call loss there. And you go back, say, I need to change all those parameters in those neurons so that I can do better next time. Through this gradient chain rule, layer by layers, and choose like 100 millions of now, before and now it's like billions, tens of billions. even hundreds of billions in the latest large language models. So what is a framework? At the bottom, you see those very important events happens in the AI, especially in deep neural network industry or communities happens. In 2012, Alex published MXNet through his own code to first show the results way better than before of using traditional machine language algorithms. 2015, another very talented Chinese researcher named He Kaiming published a paper on ResNet 50. You probably have been hearing again and again over the past few years. It is the first time that showed that you can train deep neural networks, can do better. As you can see that in 2016, many open source frameworks comes out from the research communities, from the industry. Among them, most famous ones are TensorFlow from Google, PyTorch from Facebook, now called Meta, MXNet from Amazon, CNTK from Microsoft, and PyTorch from Baidu. Those are big names. 2017, which is the year I joined NVIDIA, one important paper was published. It introduced a model called transformers. It shows you can train very large models and sequence models to nowadays called large language models. It takes quite a while for engineering team and researchers and industries to realize it can do important things. In 2022, ChatGPT comes out. It turns out it stirs a big wave in this AI community that, wow, this is a real thing. If you have joined GTC, this year GTC at San Jose, you will see how many people are there from so many industries. They're excited, they're worried, and they're also waiting for what's the next. So what does a framework look like from software engineering point of view? Among that, I listed here as a PyTorch, which is one of the most popular frameworks now. It's a software project using multiple languages. Among them, most popular one is Python script. It turned out Python is most popular in this research communities, so they can try new ideas. If fails, they know where can they start, where they can check their errors. But underneath, there are many other components play a very important role. We all know, like AI models need to run powerful machines, taking days or months to run. So the performance in terms of speed matters. That's why a huge number of code was also in C++. And also most important of all for NVIDIA is the CUDA code. It shows about 4% here, but excluding all the libraries we built at NVIDIA, it probably way more than half of the code right in the CUDA. So that not only can run, but it can run faster, so that researchers and engineers can try their new ideas, come with better results. And it usually delivered in the Panda package, PIP packages, or as us, our team, we deliver a Docker containers, so that if you have powerful machines, you can pull the containers running out of box. Not only runs, but also we have examples in it. Next page. If you go to NGC, register free, you can download all those containers. Back in 6 or 7 years ago, it was only the frameworks, because you can try, most researchers can try the ideas, build the models. Nowadays, you have almost everything. You have ChatGPT models, Llama 3 models, even some of the new coming BioNemo, you can try your medical related drug discovery models there. It's all kinds of models right there. If you want to start, have hands-on experience, this is a great place to start. So I want to talk a little bit, as engineers, we want to know what's the problem, what do you have to do, rather than it's very complicated. Frameworks deal at the very bottoms 3 important things. There's compute. In the software, it's called operator, meaning you do operations on data. Whether it's come from image, your text, your language, the data. The next one, the data type. Different from other softwares also do the computations. The data types in terms of dimensions, it's huge. It can be 1 dimension, 3 dimensions, a lot of tensors coming from 4 or 5 even bigger dimensions. And it's a lot of tensors coming through this deep learning frameworks back and forth to consume your compute. Besides that, we need to help, since there are so many computations happening on, you have to organize them in a certain way that your computer will run more efficiently. You don't waste your $100,000 computers waiting for doing nothing or wasting. But what's different from, I also have other compute softwares like NumPy, SciPy things I do. What's important is there are unique operators being introduced for the AI community. This is what I asked ChatGPT, how many types of operators in a PyTorch, the most popular frameworks. There's about dozens types, which contains thousands of operators. Each one of them will also fit multiple types of data to fit in. Among them, if you want to claim as a framework, you have to deal with your tensor-related operations. You create tensors, randomize them, you do index, you cut the tensors with your types, and you put them together, all those kind of things. There are also the categories of one type of operators you might not easy to parallelize. Engineers spend a lot of time to optimize those tensors, to using their genius to, we can actually parallelize some of them so that they can run on our accelerators, such as GPUs. Neural network operators, activation functions, which is also important for artificial intelligence. You have those activation functions actually helps you to learn. And optimizers, how you opt these tens of billions of variables efficiently. Most important, I will talk about the convolution because it kicks the train of this AI revolution. Convolutions was inspired by your human's perceptions ideas. Early on, before convolution, people think about those fully connected layers, meaning every node, every data was connected to the next layers. Well, humans are using those receptor areas to recognize things. It turns out the convolutions can do way better than the original fully connected layers. I have these demos, like if you think of an image as 2D, which is as 3D images, it's a large set of data in a 2D grid. You have this called a filter, the convolutions on your image. Check, 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 check. Each one do a lot of multiplications and summations, a lot of them, and have many those filters. And you go scanning your images. A lot of operations happening. And also multi-layers too. Think about this like digits recognitions. I like this to do object detections. It was the standard if you want to do image or video related task or AI task, ranging from image classifications, object detections almost everywhere, object segmentations, posture estimations. This is probably very widely used AI technologies so far in the industry. So how do we get involved? What was our role at NVIDIA to get involved, to enable people? It turned out writing efficient convolutions, which is compute intense, it's not that straightforward. We appreciate that those early researchers not only be able to do research, but also doing the program. We as NVIDIA, we have GPUs. Ever since CUDA comes out, we can do accelerations. We have been doing a lot of matrix multiplies. Engineers from our team, deep learning frameworks teams, come up with ideas. We can actually accelerate this by turning into the matrix multiplies. And we have done a lot of optimizations to do matrix multiplies. At its core, every acceleration, hardware accelerated core, they can do matrix multiply very well. I want to mention, this month is just the 10th anniversary of this probably most widely used deep learning AI libraries. Nowadays, it grows as a standalone team and keep growing, adding more operators inside. But we came here. We'll not forget that we came here, and we're moving a long way to enable the societies and the communities to grow better. Not only we free researchers not writing those code. Every time NVIDIA release hardwares, besides architecture, we also release different type of GPUs to suit your different workload, and they price differently. Ranging from a little device on the edge, have only a gig or a couple of gigs of memories, very low energy, to all the way to data centers. Hundreds of thousands of GPUs running as like giant GPUs for your high-load AI workloads. And deep learning framework sitting on top of this, all those NVIDIA libraries, not only to make sure it works on only one type of GPUs, but all kinds of GPUs, so that the user doesn't have to be worried about where should they change. And also coordinate different libraries that we'll talk about later, that they can do it together. So back to the framework itself, why there were so many before, and if you see my previous slides, in 2016, people realized that deep learning can be a thing. And companies and researchers say, oh, we gotta do this. We're gonna have some, if we don't do this, we will not have an advantage of doing AI research. So there are companies up, like Google, the big names, to do their TensorFlows. And PyTorch wants to catch, Facebook wants to catch up and do the PyTorch. So there's little difference. Although they do the same thing, they approach the problems differently. In order to do AI or model, your AI models, you need to build them. And it depends on at what stage you want to build them easily, and you also want them to perform very well, meaning run faster. There is a compromise to do either one. One thing might be a little technical is, early on, when TensorFlow comes out, you have to build the static graph. Build it first, and use the TensorFlow to speed it up. It turned out it's very hard for researchers to tune this stuff, to check which parts goes right and which parts goes wrong. And PyTorch comes with these ideas to say, I can build a dynamic graph that can check at each step. And that has great feedback from research communities. Well, I personally be the MXNet deep learning frameworks managers for a while, even though we still do some kind of thing. They found we can do both. Like we can do static mode, symbolic mode, or imperative mode, and having those hybridized things. I'll not talk about how the fate will be, but gradually they are coming towards the same goal. They can do both. They enable researchers to easily design the models, run the models, check the models, but also behind it, it can optimize through the framework. So we, deep learning frameworks at NVIDIA, what can we do uniquely? Remember early on when Volta comes out, the more you buy, the more you save things. How can we achieve the best performance ever? It claims to have 1 petaflops compute through the mixed precision. All the evils hide in the details. It has tensor core, but enable the user to use the tensor core is not straightforward. If you have been in the compute industry, you know the floating points, the numbers, naming floating points are represented in different ways. In high performance compute industry, it's pretty common to represent in double precision, which uses 64 bits to represent one number. Well, in AI, it's very common to do it in 32, cut in half. And most of the papers and the benchmarks are done in FP32. We have to demonstrate that tensor core can speed you up, but not losing accuracy. The problem is there are 1,000 operators. There are some of the operations computes may be okay, while the others may be not. If you know a little bit about how those floating points, numbers, representing the computer, different bits shows different challenges. If you have more bits, you can represent more numbers, and it can have more represented along this number axis. So there are two challenges there. AP16 represents less numbers, less dynamic range, and also when you're coming back to learn, it also may lose some of the capture, some of the gradient descent problems. It took our team 2 to 3 years to showcase, oh, we can do actually most AI models faster, but not losing accuracy. I still remember this, they were trying to convince people, you can use Tensor Core using these packages, but not losing accuracies. It turns out nowadays, fast forward, people are accepting this low precisions. I haven't mentioned that why we need low precisions. It has multiple benefits. Besides compute, there's a lot of data movements. It can also cut the data half. Think about it, you have a model of 100 gigabytes, and now you cut it in half. And you reduce the data movement, not inside GPUs, inside the compute, when your machines. Nowadays, the model has to cross multiple GPUs. You reduce the traffic of the networks. So NVIDIA comes more Tensor cores. And Volta, we have successful Volta by thousands of engineers works and have more Tensor cores. AP16, we're coming off Hopper, H100, which is the most popular hardware in the market, using FP8. And I would expect this to keep going on. Not to the 1 bit, but this will keep going on. Well, the new times comes out, the new challenge will come along too. Engineering teams like us will hope to tackle those problems. So what else? Instead of speeding up the compute, if you have done any optimization on any compute softwares, you want more compute at the same time, parallel that. Also, the memories matters. How do you access the memory matters. When you want less. If you know the computer architectures, you know this memory architecture. When you're trying to load or write back to the data, it's actually not one. You do pages. All those memories are in pages. You want less to do less load and write back. If you know a little bit, the loading and saving back compare with your computation. So it's hundreds to 1. It took you hundreds clock cycles just loading and saving this data back, while your compute just faster. You want to reduce that. So we come up the ideas. We have to understand the data layout inside the deep learning frameworks. Here's the NCHW to NCHWC, which is very popular in image and video related tasks. It turns out if you do NHWC, put in the channels first, you can improve your performance by 20% or more. So we're not stopping there. Once you get those on the GPUs or on the machines for the compute itself, you think about, we realize the data loading becomes bottleneck. This is how we deal with problems. What's your bottleneck? You do your top priorities once. I solve this. What's next? It turned out when you train a large model with a lot of data sets, data loading also takes significant amount of time. Early days, those operations like transforms are happening on CPUs, like your crop image, your mirror image, your decoding. Those data optimization algorithms are happening on CPUs. So NVIDIA has the LE project, which actually from our team, studied from our team, we got a couple of engineers say, okay, I can reach only 19,000 images per second on our GGX2. Can we push better? Can we reach 20,000 or even more? So a couple of engineers studied ideas, and then gradually we built a whole team in Poland, and this team is flourishing. This is probably the most popular data learning libraries if you train an image or video related task. So what's more, can I do better? The model is growing bigger and bigger. If you train a model, and there's one thing you cannot avoid. Those GPUs need to talk, those machines need to talk. Like not one time, many times. When you do forward, there's forward and there's backward learning process. Those computers need to talk to each other. Previously, in the HPC industry, you cannot, separate like point to point, like two machines talk to each other. Well, in deep learning in AI, it turned out all the machines need to talk to everybody. How can we do that? So this is actually the original idea is coming from a group. And the first is called NVIDIA Collective Communicate Libraries can solve that using those ideas of ring-based without like one machine has to wait another. They all connect with each other so that we can improve the performance on a single node multi-GPU or multi-node trainings. Nowadays, training happens on tens of thousands of GPUs. Imagine how important this library is. I am proud to be in the team. And it keeps growing that this will be the standard if you want to train the large models across many machines. So, being a deep learning frameworks early on, we're kind of like central point to connecting with low-level libraries and our high-level applications. A little different from all this work I've been doing before, I've been saying before, our open source project. We get it done, we deliver to open source, we can have it. Another thing we're also being part of it is called MOPERF. MOPERF is a non-profit organization to showcase the current hardware and software together as a systems. How fast can we train a well-known model like GPT-3, Llama, early on Resident 50, all those ones, with all the optimization you can go. That's opened a pioneer. We have a pioneer group to see what else can we do. Can we do better? It turned out the operators we're talking about, it can be fused. If you've done any optimization works, you say when you fuse, reduce the data movement, keep locality, can do more. When it comes to the multi-node, thousands of machines with tens of thousands of GPUs, to training a large models also bring another challenges. You might know, like, have mini batch trainings. You go every one machine to training some of them and adding them together to as big batches. With large scales, you want the batch to be very small. But it's not good for GPU, which means you stay less time on running the compute, but more times on transfer of data. So there are a lot of ideas coming, like such as group batch norms come into play. I think my point is, this will push the software engineer to another ground. Can you come up with the solutions to solve the new challenges? Early on, all those frameworks claims they are end-to-end. What does that mean? Meaning you can design the models on the frameworks. You can train a model with the frameworks. You can also deploy your models in the framework. It turns out that they all works. It turns out the training and the inference has different challenges. For example, the inference, some of inference means real time. If you want to detecting a person, a car, in a real camera, you want to be very fast. You want real time, low latencies. While training, you don't care. You just put it in the data center. You can train hours, days, even weeks on that. As a framework, it's kind of diverged now. Can we do something specific with training, while the other things specific for tensor for inference? I think at NVIDIA, I think Jensen has been talking about it. We know that inference it's important. As inference that will affect most people's life. When you use an AI, it happens inference time. We build frameworks for training to enable these AI communities to do their researchers' designs, or inference is even important to affect more people. So there comes idea or product named TensorRT, was specifically for inference. Every software needs a period of time to get it done. Early days, like frameworks are responsible to make sure TensorRT runs. It cannot run itself at the beginning, and we spend a lot of time to make sure it runs in the framework. We train a model and sending some of the operations on TensorRT, it runs faster, so the user can run a faster inference models, like low latencies, real times. And gradually, this TensorRT grow bigger and bigger. And nowadays, there's one product from TensorRT called TensorRT LM. So you can run your inference language models through this piece of software and take advantage of all this GPU powers there. This might be a little bit technical, why inference is a little different and why it's challenging. I talk about FP16s, cutting in half, right, was 64-bit and double precision, 32 smaller FP16, and even go FP8. Inference, you want even smaller. Not only save your compute, but also save your energy. At the end of the day, you want to save faster and also save energy. But the challenge goes to software engineering. The model was trained with a floating point numbers. Can you go with int8? We spent years to make sure that trained models with floating points can actually run on this int8 model. We call it quantize and dequantize. From a floating point to int point, you have to quantize them. They have different dynamic range. And also they're not evenly distributed on this number axis. I will not go into detail, and then through this, you can actually speed up your inference by a lot. All the work happens under the frameworks. What's more, more and more frameworks, like almost all the frameworks are in open source domain, so you can use them. It turns out most of the frameworks are doing similar things. Now, we have multiple libraries available at NVIDIA. Every framework are free to adopt those ones and keep growing. And things you have to enable more operations, more new deep learning models coming into the frameworks, is keep growing. Well, it's become more and more consolidated. Nowadays, you probably see PyTorch very popular on this research AI engineers, TensorFlow in productions. Some of the early frameworks have been sunset, like Caffe, MXNet. Well, new things comes out, as I mentioned. The compiler-based software frameworks is coming out. The idea behind it is I can use compiler technology, if you do the software, to optimize the original script, AI script, to take advantage of all this compute. It's also democratize that your AIs so that it can be accelerated on all accelerators. And at NVIDIA, we're also participating at those efforts too. Although we want people to use GPUs, but we embrace that people have concerns, especially when this framework is growing bigger and bigger. We need to find a way to solve them. And this Lightning Thunder's coming out like a few weeks ago. We are engaged with the team to enable that. They can actually find the best kernels, best algorithms inside our libraries to do the training and inference. What's the takeaways? I think we're in a very good time to witness AI technologies that impacts so many industries, almost touch everybody's life. And I would expect this will be years to come, if not decades to come. We're in the age of pursuing the AGIs. I'm a believer. Looks like we can do deeper neural networks. We can using more data to train better models. The multi-models comes out almost every other week, if not days, new models comes out. Remember, those are not silver bullet, that one magic thing. It's a recipe. These things can only get better. That people comes new ideas. And it's a piece of software. It can only get better. Well, being a framework team, we're helping to build the foundations and lay the bricks. And we enable the researchers and AI communities to do their job better, to do their jobs efficient. And this framework is coming consolidate so that you don't have to learn multiple frameworks to do your job. And NVIDIA's keep building their libraries. What we found, we actually do innovation inside our organizations to make sure that you don't have to do that job, you don't want to, or spend too much time, so that you can focus on your work. And there's still new technology comes out that we'll keep an eye on. We'll engage with open source community so that we all benefit with this round of AI innovation. With that, thank you.
So now we will have a brief 5 minutes time for Q&A. So any audience have a question for Dr. Cao? You can take this chance.
I am Dr. K.R.S. I want to ask you about medical image analysis, where the technology that you are developing in NVIDIA could be used using what's called case-based metrics and then analysis, which is common for brain imaging, brain tomography, etc. And how efficiently can you do the processing, especially if it's case-based.
Could you repeat that one? Why is it image related?
No, it's called case-based. When you do medical imaging or NMR on the brain,
right?
And what you get is what's called voxels, and then you do all the imaging, and when you do the imaging, you get what's called a case-based metrics.
Right.
Okay. And you need extensive analysis depending on what you need to get the output better than doing the radiology analysis, etc., which can be done using AI, to the level that you are doing, which is very, very important, not only for medical imaging, for any other body imaging also. Are you into that? Are you working on it?
Honestly, I'm a engineering side. We do get into the research side, but I think the point is, by doing this AI, you can learn from your knowledges. Especially for those imaging related, like the cancer detections, and they having those experts to run those images to identify the ground truth, and you learn from this to early detect for what's happening on those images, especially like high resolution ones, the big ones. I don't know exactly what the algorithm is talking about, probably very specific for image detection ones, but with more data available, with large models we can have that, it already shows that those AI models can on par or beat some of the experts in this domain, in the image domain. This is happening and it keeps improving. Yes.
Due to limited time, we have to end the Q&A session now, but Dr. Cao is still going to be here, so you guys can basically approach him after the break time, and then have more discussion.
Thank you.
So, Dr. Cao, please remain on stage. We are going to present plaque to you. Dr. Cao, please remain on stage. Yansu or Li Bo, please come forward. Raymond, can you represent CIE to present the plaque? thank Dr. Cao once again for his wonderful speech.